Okay, let us begin. Our today's speaker is Ikeda Yasushi, and he will speak about, you see the title, Quantum Argument Shifts in General Linear Algebras, and I want to know that this is Yasushi's doctoral thesis, so any remarks and comments are quite welcome. And let us begin now. So, Yasushi, you are welcome. Please begin.
Uh, uh, Thank you very much for giving me this opportunity. So, here is my plan today. First, I'm going to explain prior research and motivation of my PhD study, and next, I'm going to introduce the key concept of my PhD thesis, which is quantum derivation on the universal independent algebra, and then I'm going to show the formula I found, and it is used to prove my our main theorem, and also it has interesting property and some application. And then I'm going to show the outline of the proof of my proof of main theorem, and as an application of the of my formula, I'm going to calculate generators of quantum argument shift algebra up to the second order. So this is a setting. So first, we consider a finite dimensional complex Lie algebra G, and its basis will be denoted by E1 to En. So it is d-dimensional, and then it's symmetric algebra SG. SG has the Lie algebra as a subspace, and SG is a commutative associative algebra generated by the elements of the algebra, and this symmetric algebra has a unique Poisson bracket, extended Lie bracket of G, and uniqueness is understood by the property Leibniz property of Poisson bracket. So if we have a product here or on the right side or left side, then it has Leibniz property, so we can calculate in this way. So we can decompose the product in the symmetric algebra. So finally it leads to the Lie bracket. And also we can show that it 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 in fact exists. So SG is a Poisson algebra, and this Poisson bracket is called the Lie Poisson bracket of the symmetric algebra. Then next we write C bar for the Poisson center of the Poisson algebra SG. And take any element Xi from its dual space, and then we can consider. So in fact, symmetric algebra is if we take some basis of the algebra, then it is nothing but polynomial algebra in terms of the basis elements of the Lie algebra. So we can consider partial derivative acting on this algebra and consider this kind of linear combination. Then this expression is independent from the choice of basis of the Lie algebra. So element of the dual space G star defines this kind of operator on the symmetric algebra. Then in 1978, Mishenko and Fomenko proved the following theorem, and it is referred to as the argument shift method. So this theorem says that if we consider any these kinds of elements where small n is non-negative integer, and x is from the Poisson x is the Poisson central element of the symmetric algebra. Then we can consider this kind of family, but any two elements from this family is Poisson commutative. So if write explicitly, then any here m and n are arbitrary non-negative integer, and x and y are also arbitrary Poisson central elements. So in formula, this term says this statement. So this is called the argument shift method. So after that, after the theorem, as a conclusion, so if we consider subalgebra in the symmetric algebra generated by this Poisson commutative family, then we obtain Poisson commutative subalgebra 6C bar in the symmetric algebra. And the second remark is that any real algebra is associated with its universal enveloping algebra UG, and the relation of the universal enveloping algebra and the symmetric algebra is expressed in this way. This means that universal enveloping algebra UG is has filtration, so it is filtered algebra, and then we can construct degree algebra, graded algebra associated to the filtered algebra, and this associated graded algebra is canonically isomorphic to the symmetric algebra, and it can be from the deformation quantization point of view. We can interpret the relation of these two algebra like the universal enveloping algebra is can be considered as the quantization of the symmetric algebra, and this is a kind of symbolical relation between these two algebra. Then so considering this situation, Binberg in 1991 asked, so since we have Poisson commutative algebra 6 bar in the symmetric algebra, so he asked if we can find commutative subalgebra in the universal enveloping algebra with the same relation as in written here. So Binberg asked this problem, and commutative subalgebra 6 in UG satisfying this relation is called quantum argument shift algebra. I'm sorry that I forgot to say that this 60 bar is called argument shift algebra or Mishenka-Fomenko subalgebra. So quantized version of this algebra is called quantum argument shift algebra or quantum Mishenka-Fomenko algebra. So after his question, there were many progress on this problem. For example, his problem is solved by Nazar and Olshansky using Yangians or twisted Yangians, and Tarasov also constructed the quantum argument shift algebra using symmetrization mapping. And Fagin-Frankel center is also useful to solve this problem. And Fagin and his collaborators, and also by Lyubimnikov, constructed quantum eigenshifted algebra for regular elements XT, and for simple Lie algebra of types A and C, Fatuni Morev, and also Morev Yakivo constructed quantum argument shift algebra. So these are prior research, and motivation of my research is to find not only quantized algebra, but also quantized operator. So these people found quantized algebra, and so, but this operator acting on the symmetric algebra is remained untouched. So my purpose is somehow construct quantized operator, and also I want to show that this has an appropriate property. So it means that the quantized argument shift operator satisfies similar property to this theorem. So and to this end, I'm going to use a quantum derivation of the universal empirical algebra, and it is proposed by Gurevich, Pyatov, and Saponov. So, but also they defined quantum counterparts of partial derivative operators on the specific Lie algebra, GLD, general linear Lie algebra. So my research is about this specific Lie algebra. So first, I want to fix some notation. So as you know, GLD, general linear Lie algebra, has this D-square basis element. So satisfying this commutation relations. So GLD is nothing but the algebra of matrix algebra. So so EIJ is abstraction of matrix unit. So matrix units in the matrix algebra satisfying this kind of commutation relation. So I choose the same kind of base element. So we have D square elements or basis elements satisfying this commutation relation. And using these D square elements, I'm going to define matrix composed of these basis elements. And so first, write the bar ij for the partial derivative with respect to eji. Then we have the square partial derivatives. So write at once in this way. Then this d bar defines a linear map from the symmetric algebra to the matrix algebra of the symmetric algebra. And this linear mapping is characterized by three conditions. First, partial derivatives kill scalar. So if nu is any scalar, then d bar nu is zero. And second, since d bar ij is partial derivative with respect to eji, so so d bar ij eekl equal can be write using Kronecker order. So we have this kind of obvious relation, and second condition is equivalent to require this Kronecker delta condition. And third, partial derivative operators satisfy Leibniz rule. So the third condition is Leibniz rule. And this matrix valued operator is characterized by three conditions. So it's quantum derivation proposed by Greb-Spiatov and Saponov is quantum counterparts of partial derivatives. But since universal enveloping algebra is non-commutative, so if we write just the same conditions, so then we cannot construct our operator satisfying the same condition as in the symmetric algebra. So they modified the third condition. So and if we add this third term, then they showed that we can construct so the operator will be well defined, and we can construct the such an derivation. So and this kind of derivation is called quantum derivation, and the modified Leibniz rule will be called quantum Leibniz rule. So they obtained similar operator on the universal enveloping algebra. Then if it is really the quantum counterparts or partial derivatives, then maybe it will be a good candidate to construct quantum argument shift operator. So let C be the center of the universal enveloping algebra, and also consider any linear combination of quantized partial derivatives. Any linear combination of this form. Tij is から。Then so it is a good candidate of the quantum counterpart of the Xi bar. So the conjecture is that this new operator Dixie satisfies the similar conditions of the Mishenka-Fomenko theorem, and in fact it turned out to be true. So and it is the main theorem. So main theorem can be formulated just as Mishenka-Fomenko theorem, but here now we use quantum argument shift operator instead of classical argument shift operator, and also within the universal enveloping algebra, and not in the symmetric algebra. And very easy corollary is that this sub-algebra generated by this commutative family is the quantum argument shifter algebra in the direction C. So here Xi is any numerical matrix, but considering the the symmetry, considering the symmetry, then we can assume that Xi is a diagonal matrix, and also diagonal elements are mutually distinct. So we have this kind of elements, and if in this specific situation, Bimberg and Dubnikov showed that the quantum, in this case, the quantum eigenshift algebra is a centralizer of the set. Yes. Centralizer means that it consists of all the elements commuting with any elements from this set. And the the proof of our main theorem is carried out by showing that this element commute with these elements, and we have done it by induction on the order of derivative. So roughly speaking, there is the proof is the proof consists of n equal 1 part, and also inductive step part. So 2 parts. So to show the base case n equal 1, we can use some formula which I found before this main theorem. So next I would like to explain about this formula. So first, the center of the universal enveloping algebra of GLD is generated by trace E to trace e to the power of e to the power d. So and also these d elements are free generator of the center. And this situation is first found by Gelfand. So these generators are called the Gelfand invariant. So now we understood the generator of the center of the universal enveloping algebra. So next we would like to calculate its shift. And uh, to this end, it 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 is at least useful to calculate this kind of elements, since this power of the matrix E uh, uh, are used to express generator of the center. So this is this is the first idea. And in fact, this point of view is successful, and there is a formula. There is a formula to express this quantum derivation of matrix elements of the power of the generating matrix E, and it is written in this way. So this is my my first result of my research on this topic. So here this kind of symbol is polynomial defined in this way, and also they have integer coefficient. So they are polynomial of integer coefficient, and also small e is a matrix, and it components basis of the algebra, so it can be regarded as D by D matrix with coefficients in the universal embedding algebra. So if we put this matrix into polynomial, then we obtain polynomial, and this operator is also matrix valued operator. So this is contained also in matrix, and this is matrix.
Yasushi, I'm sorry, I
yes.
don't understand the notation. In this main formula, the first summand, so F plus, and so on, and then E in brackets, and then J. What does this mean?
You mean here?
Yeah, in the middle. Yes, in this summand and the term in the middle. E in braces, and then is it a subscript or
You mean
yes,
the
yes.
yeah, I see. I explain.
Mhm.
So uh so so here f plus n minus m minus 1
Mhm.
e, and also e to the power of m, they are matrix.
They are matrices, yes.
Yeah, in this, and I write sub j for this is definition, and this is vector and
Just yes, the jth the
yeah,
column, yes.
yes.
Uh-huh. Okay,
So
thank
so
you.
so
Yes, I
yeah.
understand. Thanks a lot.
Yes. So and so this is this kind of vector, and this is an opposite. So this kind of operate.
Yes, I understand.
So, okay. So so again, this is matrix and matrix. So everything is consistent. So so proof is not uh, uh, proof is the following. Uh, so 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 assume this form, then calculate the next step. Then here we have matrix product, so n power, and also here we use quantum Leibniz rule and so on, and here and next we use commutation relation, and after that we can obtain the 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 same form for the n plus one order. So I'm sorry that I didn't write, but as a result, so assuming this form and calculate the next step, then again we obtain the same form, and also we can see the relation between nth order and n plus one order. Then from this relation, we obtain the recursion relation. Uh, uh, so relation between nth order and n plus one order, and here is the obtain the recursive relation. And the solutions of this recursive relations, GMN and HMN, can be written polynomials written here. So the solution of this recursive polynomial recursive relations written in this way. So this is the proof. So now in this way we obtain formula. So it can be used to prove the base case of our main theorem. So and one remark is that we just considering getting the some some term and modify the operator d in this way, then then this corresponds is not only linear but also preserve any algebraic operation. So this this mapping preserve multiplication preserve multiplication on over here and here. So this modified operator is not only linear but algebraic homomorphism. So it is more it has more convenient property. So for that reason, I like to write D for this modified version of this operator. Then now modified operator is algebraic homomorphism, and if we write 6C sub n subalgebra generated by the quantum eigenshift up to nth order, then first this is typical central elements in the universal and vector algebra, and using the formula I just showed, then quantum and here this is modified one, modified. Then we can apply the formula, and since now this is algebraic homomorphism, so we can calculate this kind of expression, and result is this. So here is nothing but a central element, and also my convention is that so here n1 and n2 and so on is from -1 to n, but trace. So my convention is this mean just identity. So using this convention, then the result is this. So here's central elements, and from here typical element is a trace of C of some power, maybe case power or something. So this is typical central elements, and this is so the first order shift, the first order shift. So it is generated by central elements, and also trace of psi e to the nth power from here. So this is the first order situation. So 61 is generated by these elements, And so 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 to prove the base case, so we need to show that this elements commute with EII, and so EII and this element. This should be contained in the centralizer of these elements. So just calculate a commutation relation, then just we obtain 0. So these elements commute with the these elements used to define the centralizer. And so up to here the base case, and also inductive step it is sufficient to show the commutation relation of operator. So first, as regards to EII, so for this element, we have this operator relation, and it is perfect to make the inductive step. But from this element, add of this element and operator DXC doesn't do not commute. But if we if we consider the commutator of this commutator with operator DXC again, then we obtain 0. And in fact, this to condition this is 0, this operator is 0, sufficient to show the inductive step. So in this way, we prove our main theorem. So now this is the increasing sequence of subalgebra, and its union is the quantum eigenshifter algebra in the direction C. So this is the consequence from our main theorem. So let us proceed to calculate the second order. The first order I calculate here. So how about second order? Then second order is also computable. And so result is this. One remark is so here operator D is remain here, but uh, uh, but this term can be also calculated. So in fact we can calculate everything to the end of this kind of this kind of the argument shift. So from this complicated expression, we can conclude that the second order, the second order subalgebra is generated by this kind of element. So this element is from this expression. So but we can say something more. So now we know the generator of the algebra 62, but in fact this is a bit redundant. So this is what I want to explain next. So first, using polynomial, I defined it before, and using these polynomials define a integer matrix as an coefficients of this polynomial. So in anyway, and then let taxi x express this kind of linear combination, this kind of linear combination, and also define this kind of easy mapping sigma. Sigma is just move from the light top elements to the light top elements to the left bottom and sum up. So obtained matrix is lower triangular matrix. So this kind of then first property is that this taxi here taxi is invariant under sigma. So taxi sigma x equals just taxi x. And this is done by this kind of simple relation, and we can prove this relation. So we have this kind of invariance. Then using again my formula, then result is that this kind of elements can be right in terms of some matrix, and this kind of elements can be written in terms of this kind of matrix, but modulo 61. And so these are generator here, generator, and from the second order. So these generator can be written in terms of some matrix like this. But I find some relation between these matrices. So they are not independent; they are linearly dependent. And satisfying this kind of relation, and maybe here is plus k plus 1 0 0 p n plus k transpose something, and this is 1/2 of sigma p m plus k p m plus k 0 0. So in fact, linear independent ones is just either this two indices are equal. So here n plus k, so they are equal, or different only by 1. So here n plus k and here n plus k plus 1. So I found this kind of linear relation. So as a result, so from generator only we need either m equal n or m equal n plus 1. So this is a new set of generators of the second order algebra. So this is my third result. And if I write explicitly, then if I write these generators explicitly, then this kind. So first trace xi square e, and then so first xi square e square xi square e to the power 3, and so on. Point is that so these generators are some linear combination trace xi e I to the power I e j, and some linear combination, and any element from this is this kind of linear combination. But this linear combination is not arbitrary. So if we consider arbitrary linear combination, then we don't obtain commutative family. So they are not commutative. But if we choose this coefficients properly, then we obtain the list of mutually commuting elements. So I found this kind of mutually commutative elements of sequence, second order, third order, fourth order, and so on. So this is my last result about this on this topic. Yeah. So yeah. This is my all result.
Okay, thanks a lot. Remarks, comments? Gosha, don't you want to add something or to comment?
Actually, just I think it is worth saying that the main purpose of the whole business is not to find some new approach to the argument shift algebras themselves, because it's a very well-known topic, you see. But what we really would like to find, we'd like to find some new operator, because this operator looks like the quantization of a vector field on, in the simplest case, of a vector field on some manifold. In fact, you can generalize argument shift method to a very vast, in classical sense. I mean, the argument shift method in the sense of Poisson algebras. There is a very vast set of examples, and in fact, this argument shift method is a particular case of the by Hamiltonian induction, by Hamiltonian structures. Nobody knows still how to quantize by Hamiltonian structures in general. There are lots of examples where you can actually raise the commutative algebra induced by Hamiltonian structure to a commutative algebra in the quantized algebra, in the quantized world. But there is no general no general approach to this problem is known. So this whole topic is our attempt to give some, maybe find this approach, to find a trace of such approach, because if it will be possible to find such operators in other situations, some general procedure, we would be able to quantize argument shift algebras in full generality, and even try to quantize by Hamiltonian commutative algebras. That's actually the whole business. I'm sorry, I missed the beginning of the talk. So I don't know, maybe Sushi made this clause in the very beginning. But yeah, I think I would like to attract the attention of the audience to the fact that the main purpose of the whole research is to find quantization of the operator.
Yes, it was stated in the beginning, yes.
Yeah. And I mean, even in the case of, and the second thing I'd like to mention is that even though we managed to find this operator, its properties and its, the reason why it works are far from being understood. Actually, one can show that if you apply this operator to the argument shift algebra, to the quantum Mischenko-Fomenko algebra, you will not get the same algebra. In classical case, in the case of Poisson algebra, if you apply the shifting operator to elements of the argument shift algebra, the Mischenko-Fomenko algebra, you will still remain in the Mischenko-Fomenko algebra, but that's not the case in quantum world. Second, we don't know independent proof of basic of the main theorem. The proof of the main theorem is based on the description of the argument shift algebra in terms of the centralized of certain elements, one, and the second, we actually needed the existence of argument shift algebra just to make sure that it will work. That's second. And third, due to all these limitations, it wouldn't be very much surprising, I think, to anybody if I say that the same method fails when we try to apply it in other semi-simple series of Lie algebras, series of semi-simple Lie algebras. For instance, one can, use some naive approach to this construction and define similar operators for the universal enveloping algebras of type B or C or D, and then check if the same theorem, same main result still holds. And the answer is no. We don't get the same result. However, if you apply these operators to some nice generators of the centers of universal enveloping algebras, you get commutative families. So somehow you still get some commutativity, but this is even less clear. It is even less clear why we get it, because it is not just we need some operator. We also need to choose very carefully the elements. So there are lots of mysteries in this research, and I really think it is worth going on there. And also, I'd like to attract the attention of the audience to the relations, to the elements which Yasushi described. You see, in the very end of his talk, this here. You see that these coefficients, they are really, they look random somehow. Although Yasushi actually gave a general formula for this operator, for these coefficients. But still, if you try to solve the equations that such elements commute, it will not be easy to find these coefficients. It's remarkable that they can be found in by general formula. And second, it is interesting that they all are integers. One can expect at least rational coefficients. But here, all the coefficients are integers. So why this is so is also quite a mystery for me. So I would like to attract the attention of the audience to this problem, and maybe somebody will explain this further. Okay.
Okay, thanks a lot. More questions, more remarks? Well, then, thanks a lot, Yasushi, and well, we're waiting you here in Moscow quite soon already. Goodbye, and thanks a lot again.
And I want to add something
Yeah, sure.
as in written in comments of Zoom meeting. In fact, calculation is very troublesome. And for example, so I explained this kind of linear dependence of between among matrices, but this linear dependence is equivalent to this kind of complex relations of binomial coefficients and also some this kind of relation between polynomials and so far this is not done by hand but just using computational software and calculating this quantum derivation is also very troublesome. So we need some effort to calculate quantum derivation, especially iterated one. Yeah, and this is just what I wanted to remark. Thank you.
Okay, thank you. Anything else? Well, then, thank you very much again, and goodbye.
Thank you very much, and see you soon in Moscow
Yeah, sure.
in 2 weeks.
Yes, okay, goodbye.
Bye.